this one always makes me laugh because I'll always try and put like visual. I don't know, like during the normal year, in stats because the prompts are so long, and I don't want you to have to worry about like writing them out. I'll print out packets of notes that you just kind of fill in as we go along. Um, and I'll always have like dumb visual puns based off the name of it. But this one just makes me laugh because one time, 15 years ago, me and a couple of my friends were walking through a parking lot going to get like Chinese food, and just out of nowhere, we walked past a car that had a sunshade with Garfield on it, and one of my friends was like, "You guys know how Bob loves Garfield? He just made this up on the spot." And to this day, I get texts from them just with like random Garfield stuff from thrift stores. I like don't like Garfield, but they made this lore that I'm in love with Garfield just based off nothing and have kept it going for 15 years. But this comic does illustrate kind of the point of confidence intervals where it's a weatherman and it says the temperature tomorrow will be between 40 below zero and 200 above. That would be considered a confidence interval. And he says this guy's never wrong. Well, that's because it's a huge interval. So something that you have to deal with in confidence intervals is balancing accuracy with precision. You can be 100% accurate, but then it's very difficult to be precise. You have a very big interval, right? You can be very precise, but then you're going to be wrong more often, right? Not very accurate. So confidence intervals, we try and balance that a little bit. And generally, you're going to balance that based off of how large of a sample you can take, right? The larger the sample, usually the better, the more confident you will be in your interval. The thing about that is in real life, it costs money to sample. It's very difficult to do, right? And time consuming. So that's how that comes into play. All right, so let's move on and just talk a little bit more about the basics. We just talked about this, but I would write it down. A point estimator is a statistic that provides the estimate of a population parameter. Remember, a statistic is just a computation made from a sample. And the value of that statistic is called a point estimate. It's just called that because it represents a single point on the number line. Oh, this is so much better now that I have a visual of like when you guys are done writing and I don't have to be like, give me a green check. All right, so we're trying to figure out some population parameter. We go out, we take a sample, we make our calculation. That's our best estimate of the population parameter. But as Sam pointed out, right, there's going to be variability from sample to sample. We're not guaranteed to get that same point estimate if we were to take a different sample. And so we want to deal with that. All right, so identify the point estimator you would use to estimate the parameter of each of the following settings and calculate the value of the point estimate. Okay. I'm not gonna go through putting this in our calculator. I've already worked these out, so I think this will just give you some intuition. Please don't write this full prompt down. These slides are available to you. It's gonna be much more valuable if you just like read along and think about what the point estimate would be. And by that I mean, what calculation are we looking to make? So quality control inspectors want to estimate the mean lifetime mu of AA batteries produced each hour at the factory. They select a random sample of 15 batteries during each hour of production and then drain them under conditions that mimic normal use. Here are the lifetimes in hours of the batteries from one such sample. So these are 50 battery lifetimes. What calculation would I want to make to estimate the mean lifetime of all batteries produced.
It would take a long time. You can add these things.
That's exactly what I'd want to do. All I would want to do is compute X bar. That's the sample mean, right? If you're trying to estimate the population mean, you would calculate the sample mean. And yeah, you could do that in your calculator. Probably easiest way to do that is put them all in a list and then run one variable stats and you can find the mean there. That's it. We would just want to calculate the sample mean, and that sample mean is then our best estimate. It's our point estimate of the population mean. Will it necessarily be the population mean? No, it comes from a sample, right? But it's our best guess so far. And so there we go. If I did that, just what Katie said, we would add them all together, divide by 50, we get 16.178 hours. Does everybody feel like they could do that if pressed? Okay. All right, I'll give you another scenario, because it's not always a mean. What proportion of U.S. adults would classify themselves as vegan or vegetarian? Pew Research Center report surveyed 1,473 randomly selected U.S. adults. Of these, 124 said they were vegan or vegetarian. This one I am going to make you calculate. What would we calculate here? What's a proportion? Yeah. Now, this isn't the population proportion, it's a sample proportion. How do we label a sample proportion? Yeah, you got it. So, population proportion, capital P, that's what we're trying to figure out. We're trying to figure out the true proportion of US adults, blah, 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 vegan, right? But what we did was take a sample. And so what we would want to compute for our point estimate is the sample proportion. Does that make sense? Steffi and Kayla, you with me? Cool. And that comes out to 8.4% or 0.084 as a proportion. All right, let's try another one. The quality control inspectors in Part A want to investigate the variability in battery lifetimes by estimating the population standard deviation sigma. So if we want to estimate the population standard deviation, what would we use to make an estimate for that? Don't get in your heads about this. Don't overthink it. We wanted to estimate the population mean. We used the sample mean. We wanted to estimate the population proportion. We used the sample proportion. You want to estimate the population standard deviation? Yeah, we take these 50 and we just calculate the standard deviation, right? Do you remember how we notate sample standard deviation? Population is generally a Greek letter, so it's sigma. Sample is just going to be S sub x. And again, your calculator could do that in one variable stats for you. And so if we threw that in list one and run one variable stats, we would just get 0.664 hours. And that just means that typically, whatever the true mean battery life is, any typical battery will vary from that above or below by 0.664 hours. All right, so the basic idea, right? Whatever the calculation you're trying to figure out about the population, you do that calculation on the sample. And you just make sure that you notate it as a sample version of that. So it's X bar for a mean, P hat for a proportion, S sub X for a standard deviation. There are, of course, any number of calculations we could be doing. The ones we're going to be mainly focused on for AP statistics is proportions and means, okay? So just like we were for sampling distributions, we'll focus in on those two. All right, so when we report our estimate as an interval of values, we call that a confidence interval. And all it does is give us an interval of plausible values for a parameter based on sample data. Plausible does not mean the same thing as possible. Plausible just means we shouldn't be surprised if any of the values is equal to that of the parameter. It could be the case that the true parameter falls outside your confidence interval, right? So what we've come up with is a plausible interval of values. And we'll talk about sort of the theory behind why this works. And it works because we know about sampling distributions. We talk about confidence intervals in terms of how much confidence we should have in the interval. And so one of the most common ones we'll use is a 95% confidence interval. And we specifically use the word confidence, not probability. And I'll talk about why in a moment. All right, so the confidence level C gives us the overall success rate of the method used to calculate the confidence interval. And so what that means is if I were to take many samples and create an interval out of each sample, about C% of them would capture the true parameter. So if it's a 95% confidence interval, if I sampled over and over and over again, and each time I took a sample, I calculated a point estimate and then surrounded it by this margin of error, 95% around there should capture the true parameter. And that just means 5% of my intervals wouldn't capture the true parameter. All right, so we're going to get to our first sort of script. Oops. That I need you guys to memorize. So you're going to want to write this down verbatim. Here's how we interpret a confidence interval. And it's just that bottom sentence starting at we. So we are C% confident that the interval from blank to blank captures whatever the parameter you're looking for is in context. So in context meaning, don't say the true mean, say the true mean battery life. Don't just say the true proportion, say the true proportion of Americans who are vegan or vegetarian. All right. Just a couple of hints. This first one's not that important to me. You don't actually have to write this. It just says some people include based on the sample data, but this is a phrase that's accepted by the College Board, and I want to give you the most concise thing possible to use. Something to note, though, is when interpreting a confidence interval, make sure that you are describing the parameter and not the statistic. So make sure you say captures the parameter, not captures the statistic. Of course it captures the statistic. The statistic is what you use to create the confidence interval. So the statistic is exactly in the middle of your interval. What you're trying to capture is the parameter. All right. So I'm going to kind of talk about why this works now. So let's say we're trying to capture a true proportion. And so if I think about the sampling distribution, so I go out and take a sample of a certain size. And if I were to do that over and over again and compute proportions for each one, I know that that sampling distribution would be normal if the large counts condition were satisfied. Let's pretend that it is for now. And what I also know is that that sampling distribution is going to sit over the true proportion, the thing that I'm looking for, right? Now, this is all theoretical, so like I didn't go out and take every possible sample of the same size. If I did, I know that the sampling distribution would look like this, right? But I went out and took one sample, and I computed a sample proportion. So I only have one of these p hats. Do I know which one I have? No, but it's a random one of these p hats from this sampling distribution. I went out and took one sample. Let's pretend it's this one. Then that's my point estimate. So here's my number line. Here's the point I want to capture. Here's the point I got. That's my estimate, right? So this is my p hat, and this is the thing I'm trying to figure out, p. Well, of course, if I went out and took another sample and computed a different p hat, I would probably get a different one of these, right? Maybe I would get this one up here next time or something like that. There's going to be variability from sample to sample. So what we're going to do is take that point estimate and we're going to add and subtract a margin of error to account for that sampling variability, right? And so I'm going to add and subtract a certain value, and that's going to create an interval. Instead of just a single point, I'm going to have this interval of plausible values. And as long as the point that I'm looking for is within that interval, then my confidence interval has captured the parameter, and that's all I'm looking to do. Does that make sense? Okay. So that's what the margin of error does. And the reason this works is because we know a few things about a normal distribution. Namely, we know how many standard deviations away from the mean capture what percent of the data, right? Do you guys remember that rule? It was from a while ago, but you know how creative statisticians and mathematicians are. They love to name their stuff really practically. It's called the 68, 95, 99.7 rule. And so we know that within one standard deviation interval of the mean, that's 68% of the data. 2 standard deviations, that's 95%, and 3, that's 99.7, right? And so we kind of invert that. And when I say invert that, I mean, okay, well, what if I went like 2 standard deviations, 2 sigmas, that's theta, come on, 2 sigma to either side of my point estimate? Well, now I should be capturing like 95% of the data within that interval. And so hopefully that means I'm 95% confident that I will capture the mean. And the mean is the parameter that I'm looking for, right? In the middle of the sampling distribution. All right. So that's the basics. What we do, we start with a point estimate. We decide what % confidence we have. That's going to tell us what our margin of error is. I haven't told you how to make these calculations yet. This is just like the theory behind it. We add and subtract that margin of error to both sides of our point estimate, and that gives us an interval of plausible values. Okay? The margin of error will depend on how many standard deviations we decide to go in either direction. Now, the more standard deviations you decide to go in either direction, the more confidence you can have. But also the wider your interval is, so maybe the less helpful it is. If I'm a weatherman and tell you it's going to be between -40 and 200 degrees, that's probably going to be correct. It's not very helpful, right? So that's where that balance of precision and accuracy comes along. All right. So we need a point estimate to use as the midpoint of the interval, and we need a margin of error to account for the sampling variability. So this might be it. This would be my point estimate. This would be my margin of error. And then generally what you'll do is report it as an actual interval. So if I actually added those up, I would get what, 0.687, 2 points, and I subtract, oh no, I did the higher one first. Let me subtract. I can't subtract that in my head. .613. Okay. And so you would report it like that. So this is my confidence interval. All right. Let's try an example here. This is going to be interpreting a confidence interval, and then also using it to find the point estimate and the margin of error. So 2 weeks before presidential campaign, a polling organization asked a random sample of registered voters the following question: if the presidential election were held today, would you vote for candidate A or candidate B? Based on this poll, the 95% confidence interval for the population proportion who favor candidate A is 0.48 to 0.54. All right, interpret this confidence interval. So we're just going to use our script. I'm going to say, we get Royal here. We're going to use the Royal we are. 95% confident. The interval from 0.48 to 0.54 contains, and then we're just going to state the parameter of interest in context. So contains the true proportion of registered voters who favor candidate A. There we go. So it's just that script. You'll do it enough times that it's second nature. All right, what is the point estimate and the margin of error? So in the interval, where does the point estimate fall? The middle. How do I find the middle? Take the average. Add them up and divide by 2. Perfect. So point estimate is always smack in the middle, so I'm just going to do 0.48. I'm going to, in this case, sorry, my point estimate is a sample proportion, so I'll say p hat equals 0.48 plus 0.54 over 2. I think I can do this in my head. What's halfway between 48 and 54? What is it? 51.51, right? There we go. So there's our point estimate. And then how do I figure out the margin of error once I know the point estimate? We know where the middle is. So if you think about it as a number line, we know that our p hat is 0.51, right? Go ahead, Sam.
So since the confidence interval is 95%, would it be two standard deviations?
It is 2 standard deviations, but they're not, you're absolutely right, but they're not asking for that necessarily. They're specifically asking for the value of the margin of error. You're correct, it is 2 standard deviations, but look. Here's our point estimate, right? Oh, you guys cannot see that very well. I'm so sorry. That green does not read. There's our point estimate. And then this distance is our margin of error, right? It's just the distance we're going to either side, which you're correct, it is 2 standard deviations, but I want just the actual value. So how do I find the distance between 2 points on a number line? I subtract them. And you can either do the big one minus the middle one or the middle one minus the bottom one. They should give you the exact same margin of error, which in this case is 0.03. The whole margin of error, I mean, it's 0.06 is the length of the interval. The margin of error is what we're adding and subtracting to either side. Does that make sense? So this is the margin of error, which is 0.03. All right, good enough. Steffi and Kaylee, you doing all right out there in the internet abyss? Okay. All right, we just did all this. Ooh, this should not say interval. These are new slides too. This should say interpreting a confidence level. All right. So here's where things get a little dicey. To interpret a confidence level, it's not a probability. And the reason it's not a probability is because you've already taken the sample. You guys know Schrodinger's cat? Have you ever heard of this? It's like the thought experiment where you have a coin flip based off of a random number generator. If the coin comes up heads, there's a cat in a box with a canister of deadly cyanide gas. The coin comes up heads, the gas gets released and the cat dies. If the coin comes up tails, the cat lives. And again, the coin flip is based off of just random inputs. And so the whole thing is, if you keep the box closed, is the cat alive or dead? And the thought experiment is the cat lives in both realms. It's both alive and dead. Once you open the box, then it's either alive or dead. So the whole thing with the confidence interval is, once you've taken the sample, it's game over. You now have your interval. The probability that your parameter is in that interval is either 0 because it's outside the interval, or it's 1 at that point because it's inside the interval. So once you've created the interval, you've opened the box. Now the cat's either alive or dead. So we can't interpret it as a probability, because once we've created the interval, the probability that we've captured the parameter we're looking for is either 100% or it's 0%. And so the way we interpret the confidence level is we say, if we were to select random samples over and over again and construct a bunch of confidence intervals, about C% of those intervals would capture the parameter. There's nothing magical about the one interval that you created. That one's either 0 or 1. That one either captured it or didn't. And so it's just another script we need to use. All right, let me see our time. Let me see our slides.
Do they give list these scripts and like the formula?
No, these they don't. But I mean, it seems confusing now. But we'll talk about them enough that
Okay, cool.
it'll just feel like second nature. This is the one that gets asked less though.
Okay.
Like anytime you create a confidence interval, you are expected to interpret it. So you're expected to do the scripted one that we just did in the last problem. You only need to interpret the level if they specifically ask you to interpret the level, and that'll happen much less often. Okay, let's see. All right, so let's go back, and in that presidential election example we just did, let's interpret the confidence level. So we just had this interval that said we're 95% confident that the interval from 0.48 to 0.54 contains the true proportion of registered voters who favor candidate A. Now they want us to interpret the level. So I would say if we took many samples used the same method to construct 95% confidence intervals for each sample, about 95% would capture the true proportion of voters who favor candidate A.
I know that's like technically close, but that seems like a major, like Nate Silver, who does all the polls for the election, like that seems like a really big interval in that context.
Oh, 100%, yes. I mean, and does this interval tell us anything about candidate A? Why doesn't it tell us anything about candidate A?
Because it could be either.
It could be either. All values are plausible. I mean, it straddles the 50% line. Now, you might say, oh, but there seems to be more values above 50% than below. But that doesn't matter because every one of the values on that interval is equally plausible to be the parameter. So no, we can't say anything about candidate A. They don't have the majority, but they don't necessarily not have the majority, right?
When you're looking at election polls, is this usually the.
Yeah, this is how they're doing it, yes.
So how do they decide which one to put on like the website or to tell everybody?
Well, what's obnoxious is there's a lot of bad statistical reporting because they'll only report the point estimate a lot of times. They won't show the interval. And so in this case, the point estimate being 0.51 makes it seem like, oh, most people favor candidate A. But if there's a 3% margin of error, no, it's just as equally plausible that most people don't favor candidate A in that case.
So polls, if when you're looking at election polls and checking them every 5 minutes on election night, it really is not telling you that much.
Well, you need to know, and we'll get into how these are calculated. What you need to know and what they need to report is like sample sizes, and they will report margins of error sometimes, but people don't know how to interpret
Well, like
those.
who they're sampling, because if you ask like
Yeah.
this neighborhood or Arcadia.
Oh yeah, it has to be representative, and that's very difficult to do and very time consuming. So that's why you have polls that tend to be more reputable than others, like Pew and Gallup, and then there's like, like news agency polls which are not super reputable, like Rasmussen or like CNN. They sample one direction or the other. They sample their viewers, and their viewership has bias.
That's so upsetting.
Yeah, you need an independent polling organization. All right. this is what we just talked about. If in any single confidence interval, the probability that it captures is either 0 or 1 once you've created it. So it doesn't tell us the probability. I already talked about this. Okay, this is what I said before. On a given problem, you may be asked to interpret the confidence interval, the confidence level, or both, and make sure you understand the difference. The interval gives a set of plausible values for the parameter, and the level describes the capture rate. The other thing is this. If you're asked to create a confidence interval, you are also expected to interpret it. You're only expected to interpret level when specifically asked for it. All right, cool. All right, so what affects the margin of error? And the margin of error, right, is how wide our interval is. And so ideally, you'd like to keep your confidence level high, but your margin of error is small, because your margin of error is how precise you're being, right? So what's one way you think you can be more precise? I'm trying to estimate the proportion of people voting for candidate A. Increase the sample size. More information will always give you better precision. The problem with that is more time, more money, right? But you're absolutely right. Increase the sample size. So that's one way. And I thought it was the first one, but it wasn't. The other way you can do it is decrease the confidence level. If you decrease your confidence level, you can get more precise. You're just saying, I'm not sure I'm going to be as right about this, right? I can be the weatherman who's like, yeah, it's going to be between 70 and 73 today. It's pretty precise, but then I'm maybe only 70% confident on that because that's a really small interval.
So, as like a weatherman, is that like part of your job to do this math?
Well, they have,
Or do they have people doing that?
yeah, they have algorithms. I think meteorologists do that, but the weatherman just looks pretty and reports it. And then what Sam said, you can increase your sample size, which gives you more information, right? So 2 ways to get a smaller margin of error: decrease confidence or increase sample size. The ideal, you want a high confidence level, but you still want a small margin of error, which is usually get as large a sample size as possible, right? And we'll go more into formulas. Like this first section isn't about formulas, it's just about the big ideas behind confidence intervals. But you'll find that as you increase sample size, your margin of error is going to be proportional to 1 over the square root of that. So quadrupling the sample size will cut the error in half. Because the square root of 4 is 2, then you'd have 1/2, right? All right, we're getting close here, folks. Okay, this is something that's important though. Here's what the margin of error accounts for. It's not, so error tends to, like when we hear error, you tend to think human error, like, oh, I screwed up. And so there is no statistical technique that can fix like taking a biased sample. That's not what the margin of error is there for. The margin of error only accounts for the fact that there is natural sampling variability from sample to sample. If you take a different sample, you're going to get a different point estimate, most likely. That's what the margin of error is there to account for. There's no statistical technique that accounts for bad sampling. Actually, there's one. Throw out your sample and start over. That's it. All right. So as we said, following the 68, 95, 99.7 rule, if I go one standard deviation, I'm going to be about 68% confident in my interval. If I go two standard deviations from my point estimate, I'll be 95%. If I go three standard deviations, I'll be about 99.7%. And so here is the general formula for a confidence interval. It's your statistic plus or minus a critical value. And all this is the number of standard deviations I want to go to either side. And then you're going to multiply that by the standard deviation of the statistic. This is a formula that's in your formula sheet. So scroll up a little bit. There you go. Confidence interval. Statistic plus or minus critical value times standard. They call it standard error of the statistic. I'll talk to you about why they use the word error there instead of standard deviation of the statistic. It's not important right now. The formula is in there. So the critical value is just a multiplier that makes the interval wide enough to have the stated capture rate. So if you want 95% confidence, what's your critical value going to be? How many standard deviations give us 95% of the data? So then your critical value would be about 2. It's not actually exactly 2. It's like 1.96, we'll find. That 68, 95, 99.7 rule is just a rough rule of thumb. But yeah, it should be about 2. If you want to be about 99% confident, what's your critical value going to be? That's it. I think I got 2 more examples I want to go through. All right, as part of a project about response bias, Ellery surveyed a random sample of 25 students from her school. One of the questions in the survey required students to state their GPA aloud. Ooh. Based on the responses, Ellery said she was 90% confident that the interval from 0.4 to 0.72 captures the proportion of students at her school with GPAs greater than 3.0. All right, don't write this down. Like, I'm recording this, I'm going to post it. Just participate. If you need to go back and revisit it, it'll be online for you. All right, so she created a 90% confidence interval. What would happen to the length of the interval if I increase my confidence to 99%? It's going to increase, right? Because we're going to have to, if we want to be more confident, we're going to have to capture more values unless we increase the sample size. But it doesn't say she's doing that. So the length would increase. I agree with you. How would the width of a 90% confidence interval based on a sample size of 100 compare to the original 90% interval, assuming the sample proportion remained the same? Okay, so she sampled 25 students. If we increase the sample size to 100, well, first of all, that's going to shrink it, right? And we said it's going to shrink it by about, yeah, because it's going to be 1 over 4 times root 4 times 25. Or sorry, 4 times n, I should say. 4 times our sample size in that case, right? Which is 1/2. So it basically is proportional to 1 over the square root of your sample size, so it's going to shrink it by half. I don't care that much about that you can come up with the proportion at this point. Once we get the formulas, you'll be able to do that, and that'll be in like 8.2. I'm more, if you increase the sample size, it's going to shrink the interval. Okay. Describe one potential source of bias that is not accounted for by the margin of error. Yeah, so that's called response bias, right? Yeah, for sure. That's, I'm gonna be like 4.3. Okay. And this just goes through. That's it. We did it, gang. First technical section of inference down.